This is a video from the Exam 1 review in my linear algebra class. Let's take a look at problem 1. Suppose we're given the system x plus 2y plus 3z equals 11, 2x minus y plus z equals 2, and 3x plus y plus 4z equals 13. And we want to solve the system using Gauss-Jordan elimination. And so we need to write the associated augmented matrix. And so that's going to be 1, 2, 3, 11, 2, negative 1, 1, 2, and then 3, 1, 4, 13. And so what I'm going to do is take negative 2, row 1, add it to row 2, put the result back into row 2. And I'll take negative 3, row 1, add it to row 3, put the result back into row 3. So when that happens, we have the following. We get 1, 2, 3, 11, 0, and then negative 2 times 2 minus 1 is negative 5, and then negative 5, and then negative 20, and then 0, and then negative 3 times 2 is negative 6, negative 6 plus 1 is negative 5, and then negative 5, and then negative 20. Now, there's a couple of options that we can do here. So what I would suggest is take row 2, add it to row 3, put the result back into row 3. So we'll start there. Now, when we do that, we get the matrix 1, 2, 3, 11, right? That's the first row. If we go to the second row, we get 0, negative 5, negative 5, 20. And then double check, negative 20. And for the third row, we get 0, 0, 0, 0. So we get a row of zeros. And remember, when a matrix is in row echelon form or reduced row echelon form, the row of zeros have to occur at the bottom of the matrix. Now, I'm going to take negative 1/5 row 2 and put the result back into row 2. This puts the matrix in row echelon form. But remember, we want the matrix in reduced row echelon form. So in the first row, we get 1, 2, 3, 11. In the second row, we get 0, 1, 1, 4. And then in the third row, we get 0, 0, 0, 0. Right? Okay. From here, I'm going to use row 2 to turn this entry, this 2, into a 0. And you might ask, well, how do I do that? I'm going to take negative 2, row 2, add it to row 1, put the result back into row 1. And so we still have a leading 1, which is exactly what I wanted, right? So I'm going to get a 1 here, a 0 by design, right? And then I'm going to get a 1 and a 3. In the second row, that doesn't change. I get a 0, a 1, a 1, a 4. And in the third row, we get 0, 0, 0, 0. And so we have, from this, we're going to have one free variable. So essentially, we have two equations with 3 unknowns. That's going to give me one free variable. So x plus z equals 3, and then y plus z equals 4. So what I'm going to do is I'm going to let z equal t. And so that says y equals 4 minus t, and then x equals 3 minus t. Okay. And then the solution here is going to be the following. Now remember, x is 3 minus t. Y is 4 minus t. And then z is t. And that's how we do problem number 1. Let's take a look at 2. Now, A is the matrix. 1, negative 1, 0, negative 2. 0, 4, 6, 0, right? And we want the trace of A transpose. So this one's pretty good. And so we're going to take the matrix 1, negative 1, 0, negative 2, 0, 4, 6, 0. And I'm going to multiply by 1, 0. So I'm looking at A transpose, right? Negative 1, 4, 0, 6, right here. Negative 2, 0. Now, let's make sure we see what we're expecting here. So we have a 2 by 4 matrix and a 4 by 2 matrix. So when we multiply these two matrices together, we should be coming up with a 2 by 2 matrix. Now, the first entry in the first row, first column of A transpose is the following. I'm going to take 1 times 1 is 1, negative 1 times negative 1 is 1, so 1 plus 1 is 2. And then negative 2 times negative 2 is 4. So that should be a 6 there. Now, in the upper right-hand corner of the first row, we get 0, negative 4, negative 4, looks like. And then in the lower left-hand corner, right, so this is second row, first column, we get 0, negative 4, 0, 0. So we get a negative 4 there. And in the lower right-hand corner, we get 0, 16, plus 36, which is 16 plus 36 is 52, right? So I'm old school, you guys. So 36 plus 16. That looks like 52 to me, right? So that's what A transpose looks like. And remember, the trace of A transpose is the sum of the entries along the main diagonal. And so here, the trace of A transpose, right, is 6 plus 52, which is equal to 58. And that's how we do problem number 2. Let's take a look at problem number 3. So let A be a 4 by 6 matrix. Okay. B be a 6 by 4 matrix. And then C be a 5 by 4 matrix. And then determine which of the following matrices are defined. If they are defined, I'll give you the size of the matrix. Okay? And here, let's start. So suppose I give you the transpose of A times C transpose, right? And then we're going to take the transpose of that. That's a good question. Okay? Now, so let's start with the stuff in parentheses. A transpose is a 6x4 matrix. C transpose is a 4x5 matrix, right? Notice how the columns of A transpose match the rows of C transpose. So can we agree A transpose C transpose is defined and A transpose C transpose is 6x5. Okay, that's the dimension of the matrix. And so when I take the transpose of it, so the transpose of A transpose C transpose is, now let's remind ourselves, A transpose C transpose is 6x5. So the transpose of A transpose C transpose is 5x6. Okay. Now, let's take a look at B. Suppose I give you C squared B transpose. Okay. Now, remember, C squared is C B transpose, right? Now, C is a 5x4 matrix. Okay? And so we have that twice. And then B transpose is 4x6. Right? So we already have a problem. Remember, C is not a square matrix. Okay? Because even if you come here, right? Even if you write this as C times CB transpose. Now, I agree, right? Remember, C is 5x4. And then B transpose is 4x6. And so CB transpose is 5x6. That one makes sense, right? Here's the problem. C is 5x4. And so therefore, C times CB transpose is not defined. No matter how you look at this. Right? You know, and I hope that makes sense, because CB transpose is defined in the beginning, but the minute you multiply CB transpose on the left by C, we got an issue. And it doesn't make sense. And then similarly, C squared is not defined. And we could even do this shorter. C squared is not defined, therefore C squared B transpose is not defined. And that works. That's fine. Totally fine. Now, let's take a look at C. Suppose we have AB raised to the third minus, and then in parentheses, C transpose C raised to the fifth, right? Now, A is 4 by 6. And then B is, here, let's write it here. A is a 4 by 6 matrix. That is true. And then B is a 6 by 4 matrix. So you do this very systematically. So AB is a 4 by 4 matrix. It's defined, right? It works. And if AB is 4 by 4, that tells me AB to the third is a 4 by 4 matrix, right? There's no choice. I hope that's okay. Now, C transpose, let's remind ourselves. Remember, C is 5 by 4, so C transpose is 4 by 5. C is 5 by 4. So therefore, C transpose C is 4 by 4. Right? And I'm talking about a 4 by 5 matrix. Okay. This is a 5 by 4 matrix. And so C transpose C is a 4 by 4 matrix. Okay. So if I take C transpose C and raise it to the fifth, that's a 4 by 4 matrix. And so if I take AB to the third minus C transpose C to the fifth, this is a 4 by 4 matrix. It's defined, and it's a 4 by 4 matrix. And that's how you do problem number 3. I want to show you problem number 5. 5 is very interesting, okay? And then we'll call it good for this video. So suppose we're given A inverse equals the matrix 1, 0, 0, 0, 2, 1, 0, 1, 0. And B is the column vector 3, 1, 2. Okay? So we're going to solve the system A squared x equal B. Okay, now this is not as bad as you might think it is, okay? What you don't want to do is start with A inverse and find A. You don't need to, okay? The way this works is I'm going to start with this matrix equation. A squared x equals B. And I'm going to multiply both sides by A inverse. And I do it on the left, right? Now, this says A inverse A squared times X is A inverse B. Okay? But isn't A inverse A squared equal to A? And so what that tells me is AX equals A inverse times B. And then what I'm going to do is I'm going to do it again. So I'm going to multiply both sides by A inverse. So A inverse times AX is equal to A inverse times A inverse times B. Okay. And so using the associative property, we get A inverse A inverse. A inverse times A, right? Times X is A inverse times B. But A inverse A is the identity. And we could do that because I'm basically saying A is invertible, right? Because I'm telling you what A inverse is. So if I take the identity and multiply by X, I get A inverse times B. And so X is A inverse times B. And that gives us insight as to what I'm going to do. So what I'm going to do is I'm going to take A inverse, which is 1, 0, 0, 0, 2, 1, 0, 1, 0. And I'm going to multiply by 1, 0, 0, 0, 2, 1, 0, 1, 0. So notice I get A inverse. When I multiply those, I get 1, 0, 0, 0, right? And then 0, 0, 0. And then 0, 0, 0. 0, 4 plus 1 is 5. And then 0, 2, 0. And then 0, 0, 0. 0, 2, 0. So, nope. That should be 0, 2. Let's try that again. And then the last one, 0, 1, 0, 1, 0. So 1. So that should be what A inverse is. And so then what I'm going to do is I'm going to take 1, 0, 0, 0, 5, 2, 0, 2, 1, and I'm going to multiply by 3, 1, 2. When I do that, I get the following. I get 3, 0, 5 plus 4 is 9, and then 0, 2 plus 2 is 4. And so, therefore, I see that my X bar is the column vector 3, 9, 4. So remember, again, this is A inverse, right? And I'm going to take that matrix and multiply by B. And that's what this guy was. And remember, when we solved, notice this is what we get. So that right there was problem number 5. And that's a pretty good stopping point for this video. So this is a video from the Exam 1 review, and we looked at problems 1, 2, 3, and 5. Thank you.